Alright, Scholar Strife doing some optimization of some volume. Um, so we're supposedly making a rectangular box out of a 8.5 inch by 11-inch piece of paper. So you make this box by cutting out equal x by x corners and folding up the sides. You want to have the greatest volume possible, and that's what optimization means. So first off, we're going to sketch two pictures. So flat piece of paper and a rectangular box. Okay. So we have 11 lengthwise, and then an 8.5 width. And then we're going to be cutting out corners here. That are x by x long. Okay. And then when you're drawing a three-dimensional box, you want to start off by just drawing a rectangle. And then you want to draw the same rectangle, kind of not lined up, but about the same size, or if you can, make it the same size, and then connect your corners. And there we go, three-dimensional box. So our height of our box is going to be x. That's the piece we're cutting out. And then we have our new length is going to be 11 minus 2x, because remember we're cutting an x from the left side and the right. And then our width is also going to be 8.5 minus 2x, because we're also cutting from the top and bottom. Okay, so this is 8.5 minus 2x, and this is 11 minus 2x. Write a model for the volume. Okay, so volume is equal to length times width times height. Okay, so v sub x, or function v in terms of x, is equal to 11 minus 2x, that's our length, times 8.5 minus 2x, that's our width, and then we're going to times it by height, which is x. Write your function v sub x in standard form. It just means multiply it all out. So multiply. So v sub x is equal to 93.5 minus 22x minus 17x plus 4x squared. That's when I FOIL the first two. And then we have an x out here. That's the third thing. And then, so that's going to be 4x squared minus 39x plus 93.5. And yes, you do have to rearrange it. Standard form, highest degree to the lowest degree. And then I'm going to multiply the x out. So our final answer for this part is 4x cubed minus 39x squared plus 93.5x. Okay. Now for graph on the calculator to find the cut length and maximum volume. Okay. So first thing we gotta do is, before we even go to the calculator, is kind of find our kind of like our limits, or kind of like how far x should go, because we can't cut 20 inches out if we have an 11-inch side. So So x can't be bigger than, so x cannot be bigger, so x is less than 5.5. And where I got that from is our length is 11, and then we're subtracting 2x, so we have 11 minus 2x. So that means x, so if I move this over, 11 equals 2x. If I divide by 2, x cannot be 5.5. But almost everything less than that is okay. And of course, x has to be bigger than 0. Alright, so we're going to look between that interval. So between 0 and 5.5. And if you haven't seen this notation before, the bracket means it could be 0, and then the parentheses means it cannot be 5.5. So it's between 0 and 5.5, but it can be 0, can't be 5.5. Alright, let's go to our graphing calculator. I'm going to use Desmos. So here, let me pause the video really quick. Alright, I paused it, and now I'm going to go to Desmos. Just in case you haven't seen this program, it looks like that, DSMOS. It's free, graphs things for you. The free part is always nice. So here we go. Here's my graph up here. I typed it in already. So 4x cubed minus 39x squared plus 93.5x. And then I'm looking between 0 and 5.5. And what I'm looking for is the local max. The local max. See, there we go. That's a good picture. So we have an upper hump. So upper hump up here. And then we have a lower hump. The local maximum is this upper hump here. And it'll tell us the right amount to maximize our volume. So it says 1.585, and then it'll give us a volume of 66.148. So whenever you use this program, make sure you select your graph, and then you're able to look at the important points. Alright, so our max is that. Let's see if I can pause the video and copy that down really quick. Alright, I copied them down, and now I'm going to go to here, and I'll show you what I got. So, my max, that's for my graph, is this. So our cut length should be 1.585, right? No, because we're human, we can't cut to 1.585. We don't have the tools. I mean, I guess we do if we had some very expensive things, but we probably most likely just have a ruler. So we're going to do 1.6 inches as our cut length. And then the max volume, using 1.6 inches, you just plug it into the formula, and that's what you'll get. So what should the dimensions of the box be to get the greatest volume possible? So I always like to do length with height. So our length, remember, is 11 minus 2x. So that would be 11 minus 2 times 1.6, which is 7.8. And then our width is 8.5 minus 2x, which is the 1.6. So this becomes 5.3. And then lastly, our height is the 1.6. So how we write this is length times width times height. And then we just put the inch through. You can write out inches or put the markings there for inches. Alright, let's do another example. Alright, you're designing an open box from a piece of cardboard that is 18 by 18 inches. Squares of sides or lengths X are cut from the corners. Create this box. Write a model for the volume B. Blah, blah, blah. What is the maximum volume? Okay, so dimensions and maximum volume. Okay, so always draw your picture. It helps. So we have an 18 by 18, and then we're cutting out X by X corners. So our volume is going to be length, which is 18 minus 2x. Width is also 18 minus 2x because it's the same. And then we have a height of x. So we multiply that out and get 324 minus 72x plus 4x squared. And then there's that x left over the side. So my formula is 4x cubed minus 72x cubed plus 324x. Okay? So now that we have our function, we put in our calculator and we look for those humps. So if we have something that looks like this, I don't know if it looks like this, but remember we're looking for this maximum hump here. So if you're looking at your graph, look for your upper hump, and then that happened to be a max of 2.999 and then 432. So this first value again is our cut length, and then this is our volume. So since we're human, we're going to have x be our cut length of 3 inches instead. And then our volume, if we plug it into our original formula, so I'm going to plug this in here, which means all our x values are 3, I will get 432 inches cubed. So my dimensions, so there's the maximum volume, and then our new dimensions are 18 minus 2x, which is 18 minus 2 times 3, 18 minus 6, which is 12. So I have a 12 by 12 by 3. And then don't forget your units, inches, inches, inches. Alright, number 2, just by looking at it, it's going to be an easier one because they give us the function. Whenever they give us the function, it's usually easy. So let's read this. Average number of eggs eaten per person each year in the United States from 1970 to 2000 can be modeled by that equation, where t is the number of years since 1970, part A, what is the domain of this function. So what values of t can I plug into this equation? Well, this only works for 1970 to 2000. So the domain, t can be bigger than 0, but and then less than or equal to 30, because that's 30 years. T, yes, from 1970 to 2000. B, graph the function. So I would use a graphing calculator, and then this is a rough sketch of what it kind of looks like. I guess I could use Desmos, but all those numbers. But I have the answer key here. Aha. So it kind of looks like that. And then there's like this lower hump here, and nothing else, because remember we're doing t equals 0 to 30. Now it's true there should be an upper hump somewhere and a lower, should be an upper hump, but that's off our domain. So this is t equals 0 to 30, and our minimum is about 25.327 with a So that's the x-coordinate, and the minimum is 222.934 eggs. So during 1995, because that's the 25th year past 1970. So this represents that in 1995, there was no tablets. There was the lowest point annual of, or lowest point, well, that's what I get for reading off my own paper. Lowest point of average annual egg consumption per person (223 eggs). Yeah, since my handwriting is terrible. So notice how this says 222. You can't just eat 222.9 of an egg, so you're going to say 223. Same thing with 24.3. You can say in the middle of 1995, there was the lowest point annual, there's the lowest point of average annual egg consumption. It was 223 eggs per year per person. Per year per person. Let's put a period there. So 223 eggs per year per person. Alright. Hopefully that'll help you with your homework.